Hello and welcome to session number 10. In this session we'll be spending the bulk of our time looking at the wave and the Schrodinger equations. There's a bit of math, there's a bit of algebra. I ask your patience. If you don't like all the math and all the algebra, just skip to the results. That's fine too. Then we'll be looking at the Bohr model, and the Bohr model specifically a hydrogen atom, an electron spinning around a positively charged nucleus, and we'll be doing an example which will illustrate the centrality of permittivity to everything we do in solid-state physics. And finally, if we have time, we'll be introducing the idea of diffusion currents. That's the second big current, along with drift current, that we'll be using throughout our discussions. But first, a wonderful performance of Pablo Sarasati's Ziegenweissen, the Gypsy Airs. We'll be listening to the last 4 minutes or so, and we'll see you in about 4 minutes. Okay, so this is a kind of a broad outline of some of the topics we'll be discussing today. We're going to spend most of our time talking about the wave and the Schrodinger equations, and then we'll move on to the Bohr model, and we'll develop an equation which tells us the energy levels in the Bohr model. Specifically, for the Bohr model relates to hydrogen atom, an electron spinning around a positively charged nucleus. And then if we have time, we'll talk about some of these other topics here: density of states and diffusion currents. But first, let's talk about a bit of a review, perhaps, some important quantities in semiconductors. And there's really three major quantities which we'll be dealing with. The electric field, E, that's bold-faced letter here, that defines a vector. The energy and voltage, which basically are the same, very similar, and the charge density, rho. Both the energy and the charge density are scalars. The electric field is a vector, and here we have the units of each of these quantities and some of the conversion factors and typical magnitude, orders of magnitude. And for the charge density, the important relationship is Poisson's equation, which we derived in the previous session. Now, what will be of interest is we're going to go from charge density to electric field to voltage, or we're going to start with voltage and we're going to go to electric field and charge density. Let's see how we do that. If we start with voltage or energy, we differentiate that to get the electric field, and then we differentiate again to get the charge density. So if the voltage or energy is parabolic, the slope, which is the derivative, would be linear, and then the slope of the electric field would be a constant. The slope of a linear function is a constant. And to go backwards from right to left, if we start with the charge density, we integrate to get the electric field, integration being the inverse of differentiation, and then we integrate again to get the voltage or the energy. Now, if the charge density is constant, the integral is linear, and then the energy is parabolic. If, however, and we'll look at, I believe, one case of that, where the charge density is linear, then the electric field would be parabolic, and the energy would be cubic. And this equation here is really Poisson's equation. It says we differentiate the voltage two times, once here, and we get charge density. And if the charge density is at 0, which we deal with quite a bit in field theory, then that equation, the second derivative of voltage with respect to position, equals 0. That's called Laplace's equation. Okay, so let's start now with the wave equation. The wave equation, either for E and M, this E and M here is electromagnetic, and if we have an electromagnetic wave or an acoustic wave or a wave function in the quantum world, the Schrodinger equation, which describes that, but they're all waves. Now, this is the kind of quintessential solution of the wave equation in one dimension. I is the square root of -1, the imaginary number. We know that the power and the exponential must be unitless, so the units of k must be 1 over distance. The units of omega must be 1 over time. K is called the wave number, and we see it does indeed have units which are 1 over distance, and omega is the radian frequency. Now, the difference between the electromagnetic equation and the Schrodinger equation is in this other relationship here. For an electromagnetic wave, we have that the velocity, we saw this in a previous session, velocity equals distance divided by time. The velocity for the velocity for electromagnetic wave is the constant c, 300,000 meters per second. The distance is the wavelength, and the frequency is 1 over the period. So c equals f lambda is the basic equation for an electromagnetic wave. And if we differentiate this bad boy 2 times, twice with respect to x and then twice with respect to t, and use c equals f lambda, we get the wave equation. And here sits the wave equation. We differentiate twice with respect to x, we bring down a k squared. We differentiate twice with respect to time, we bring down a w omega squared. I should mention here also, just parenthetically, that this is a wave traveling in the positive x direction. If it was a wave traveling in the negative x direction, the minus would turn into a plus. Okay. And then, of course, these, we equate them, and we use the fact that c is equal to omega over k, and then we get the electromagnetic wave equation, and here it sits right there. Okay. The units, of course, of c are meters per second, and the second derivative would be meters to the minus 2, and that's why these two things give us a unitless, and this is, in fact, is indeed the case. Okay, so now let's take a look at the Schrodinger equation. The Schrodinger equation, we also have a wave, but it's not the same as the equation here. This describes either the time variation or the spatial variation. For the Schrodinger equation, instead of having time or spatial variation, we have this thing called the wave function. And instead of this relatively simple equation here, velocity equals distance divided by time, we have the de Broglie relation. And the de Broglie relation says that the momentum is equal to Planck's constant divided by lambda, the wavelength. Now, where does this come from? In, I believe the year was 1905, Einstein said that waves, specifically light, photons, are really wave packets. In other words, waves are not waves, they're actually particles. And that's the famous expression, energy equals hf. De Broglie turned it on the whole thing on its head and says, okay, Einstein says that waves are particles, therefore I'm going to claim that particles are actually waves. And I believe his thesis was about a half a page long, and his PhD thesis, and he got the Nobel Prize for it. That's the equation right here. Okay, so lambda back here, we substitute, instead of lambda, we substitute 2 pi over k, and we get that k squared equals p squared over h squared. And that's the equation which we're going to use. And therefore, we take this simple equation right here, the wave function, and we differentiate it twice with respect to x, and we bring down a k squared, and then we substitute for k squared, and we get equation 511. Equation 511 refers to chapter 5, so that's why most of the, in fact, almost all of the equations in this session will be referring to 5.1, 5.2, 5.3, chapter 5. Now the kinetic energy is equal to 1/2 mv squared, but we have an expression now for momentum, which is just P. Momentum is P, and we use, so we substitute P for mv squared, and we get P squared over 2m immediately. And then we substitute this equation into here for P, and we get the second derivative of the wave function with respect to x squared is 2m over h bar squared times the energy. And this is just the time-independent Schrodinger equation. So really we have done very little. We simply used the wave here, basic relationship for a wave, and the de Broglie relationship, and we've been able to essentially derive the time-independent Schrodinger equation, and we generally write it in this form here by bringing this left side over to the right side. Now to continue, we go back and we use the relationship of energy is equal to P squared over 2m, which we derived previously. And of course the energy, the Einstein relationship says that the energy is equal to Planck's constant times the frequency, and the frequency is omega, the radiant frequency, divided by 2 pi. So the energy is the Planck's constant with a little bar, h bar, we call that, times omega. We differentiate this twice with respect, I should say we differentiate the wave twice with respect to t. Over here, let's see, wait a minute, over here. Actually don't. We differentiate it once. We only have to differentiate it once because I'm basically only looking for an E, because I'm going to use that in equation 513. So I only have to differentiate once. In the wave equation for electromagnetics, I had to differentiate twice. In the Schrodinger equation, I only have to differentiate once to get E, and I substitute that into equation 515, and I get immediately the time-dependent Schrodinger equation. And that's a big deal. Electromagnetic equation, I differentiate twice to get the basic equation. In the Schrodinger equation, I differentiate twice with respect to x, but only once with respect to time. And this is the famous Schrodinger equation. And I hope it really wasn't all that difficult to essentially derive. Now, Schrodinger derived this, I believe the year was 1927. It was 2 years after Werner von Heisenberg came up with his matrix approach to quantum mechanics, and this really threw everything on its head. It says that we don't need the matrix approach. We can also deal with quantum mechanics from a wave perspective. And like I say, Schrodinger equation was, I believe, developed in 1927. Schrodinger was a young fellow. And the story, as it is passed down to us, is actually kind of interesting. He went on a blind date. And well, if you and I go on a blind date, we generally would go to a movie, we'd go to perhaps have dinner, but in his blind date, he skipped all that, he went right to a hotel, which is kind of interesting. This is 1927, not the 1960s. And the story, again, as it's been passed down, the blind date either went so well that he was so inspired by this wonderful woman that he was with that he was inspired to write the Schrodinger equation. The other sort of perspective of the story is he was so disgusted with this woman that he basically said, that's it, I'm out of here, and he isolated himself and he wrote the Schrodinger equation. I prefer the former because it's much more romantic, although both interpretations have received a fair amount of support. The problem is that the woman that he was with, has essentially disappeared from history, and that's kind of a shame. There are a couple of modifications to the Schrodinger equation, specifically in 3 dimensions. This is the one-dimensional wave equation. In 3 dimensions, this guy here becomes the Laplacian del squared, but it's the way we usually write it, and it's essentially the same thing. This is in 1 dimension, and this is in 3 dimensions. And also, another modification is that this term here is associated with the momentum, with the, the kinetic energy, because del is associated with momentum, and generally then we'll add in the potential energy, and so we have a more complex term on the left-hand side, and all of this stuff in the parentheses we call the Hamiltonian. So this is the equation as it generally is written, but again there are 2 derivatives with respect to position and 1 with respect to time. That's the basic essence of it. I also have a little bit of mnemonics here, or tools, how we memorize the Schrodinger equation, but I think one of the most important things to keep in mind is that there is 1 differentiation with respect to time. Okay, so now we're attacking the Bohr model, or the Bohr theory. What this is a hydrogen atom which consists of a positively charged proton with a negatively charged electron spinning around. There is an attractive force because they are oppositely charged, so that the proton is trying to pull the electron in. That's indicated by this arrow here. And there also is an angular acceleration. The angular acceleration is given by v squared over r. You may recall we did this in session number 2. V squared over r for circular motion has the units of acceleration, meters per second squared, or centimeters per second squared. It's all the same. And the reason is that the units of velocity are meters per second. Velocity squared, meters squared per second squared, divided by meters gives meters per second squared, multiplied by m gives the angular force, or the force which pulls the centripetal force which pulls the particle in. That must be supplied someplace, somehow. In this particular case, it's supplied by the electrical attraction. So mv squared over r is the centripetal force, and what the Bohr hypothesis claims, and I believe this was well before the Heisenberg theory or the Schrodinger equation, probably in the first decade of the 20th century, is that mvr, the angular momentum, mv is linear momentum, angular momentum is linear momentum multiplied by the radius, and the angular momentum is quantized. It's equal to an integral number, and it's just an integer, 1, 2, 3, 4, etc., multiplied by Planck's constant. In this particular case, we're using h bar, which is h divided by 2 pi, but that's probably not terribly relevant for our discussions. The point is, it's from this point on, it's all algebra. It's a little messy, but let's go through it. Take a deep breath. Okay. So first, what we do is we square the left side and then bring the r over the right side. And we have this equation. The reason we do that is we'll be looking at mv squared. We're going to be isolating it. So now let's go back to this equation. Q squared over kr squared, mv squared over r, which is right here. Bring the mv squared to the left side of the equation and just flip the sides. 1 over r is equal to q squared over kr squared divided by mv squared. Okay, so now what do we do here? We write this equation again, and we multiply and divide by m over m, bringing this m in. So now we have mvr all squared, which of course is the angular momentum, and we have this extra m, this guy over here, which appears on the numerator. And so finally we have r sub n just by flipping this, flipping the left side, flipping the right side, and it's quite clear, and then just substituting explicitly for the angular momentum is equal to an integral number multiplied by h bar, and that's an important equation. The radius, or the radii, are also quantized. We can't have any radius of this thing going around. They're not, you can't have radius here, radius here, radius here, radius here, radius here, out to infinity. We have to have quantized. Jumps, 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 jumps. So the radius is quantized as well as the angular momentum. Now, let's go back to the angular momentum. This is the angular momentum on the left, equal to integral number of h bars. So we have immediately solving for the velocity. The velocity are also quantized. We can't have any velocity of an electron spinning around a proton. We must have quantized velocities. And we see that simply by dividing by m r sub n. And now we substitute in for r sub n. Where is it? Oh, it's up here. And we just stick all this stuff in here. This is all r sub n right over here. And finally, we get that the v sub n's, and we'll see why we do that in just a second, the v sub n's are equal to the q squared divided by nh bar k. You see 1h bar cancels out with the square here, leaving 1nh bar on the bottom. Now, why do we have q squared instead of q1 times q2? And the reason is that the electric charge of a proton is precisely equal to the electric charge of an electron, namely 1.6 times 10 to the minus 19th coulombs. So that's why we square this rather than having two separate charges. Now, the kinetic energy, of course, we know is just 1/2 mv squared. Well, here's v. We square it, square all this guy, so we get q to the fourth, and m we bring down, q to the fourth over nhk all squared, and of course the 2 comes there. So this is the kinetic energy, and it is also quantized. Now, for both the gravitational and the electric fields, the energy is inversely proportional not to the radius squared like it is for force, but rather to the first power. That's something that perhaps you might want to review from your high school physics, or perhaps first year college physics. Thus, the potential energy has the same form as the kinetic energy. And here is the potential energy minus q squared. The minus, I'll just explain in a minute. Minus q squared over k r sub n. This is, if it was a squared here, this would be force. Since it's to the first power, it is energy, and the reason it's minus is because the lowest energy is the lowest possible state. We call that the ground state. That would have the smallest possible radius. So we simply take now r sub n, we substitute for r sub n, must be here somewhere, here it is, r sub n up here, and we find it's equal to the mass q squared over 2 nh bar squared k squared. So basically what we've done here is we have an expression now for, oh, here it is. Sorry about that. For r sub n, we substitute for r sub n, and we get equation 5.3 5.3, and look at equation 5.30 and compare it to 5.29, they're the same, except for the factor of 2. So if we add them up, since this guy is bigger, we have a negative sign here, and we bring down a 2, which is like, it's basically the same form, except this is 1/2, and this is 1, so that's where we get the minus sign, and it's 1/2. And we note the dependence on the square of the permittivity. The permittivity would be in the numerator, because K is equal to 1 over 4 pi, I believe it's 4 pi epsilon 0, if it's a hydrogen atom. Okay, now here's a problem which illustrates all of this stuff and ties it all together, and we're going to actually do an example of this. I hope you'll find it interesting. We first note that the nth energy level of the quantum state, this is energy, this is the net energy, is equal to m0, this is the rest mass. E is simply the electronic charge. I could have written Q, doesn't matter. Generally, if we're talking about electron charge, I'll write it as E, but we can go back and forth. Notice it's not the E in the exponential, it's the electronic charge. And divided by, here I'm going to write out the permittivity in its explicit form. So I take K squared is equal to 1 over 4 pi epsilon 0 squared, the 2, and then the NH bar squared. So this comes from the expression that we derived after a lot of heartache, but at least we derived it. So hopefully this becomes reasonable. And now we look at, or we try to answer some questions. So these are just the different parameters here. M0 is the rest mass, E is electronic charge, epsilon permittivity, and H bar is Planck's constant divided by 2 pi. And these are all the values which we're going to substitute in just a minute. And we're asked the following questions. Show that E sub n has the units of energy. Oh, it doesn't look like energy here, does it? Well, that's our first problem, to show that it has the units of energy. Show that the ionization energy of a hydrogen atom is 13.6 electron volts. That's a big deal. Ask any engineer what the ionization energy of a hydrogen atom, he will immediately tell you that it is 13.6 eV. He might not know his anniversary or his wife's birthday, but he does know that the ionization energy of a hydrogen atom is 13.6. That's quite characteristic of engineers. And what that says is how much energy it takes to strip an electron from the ground state, where n is equal to 1, to its position where it's completely free of the hydrogen atom, where n goes to infinity. So we just stick in a 1 here, and that will give us, in fact, the ionization energy of hydrogen. Okay, show that the phosphorus atom acts, I should have italicized this, acts like a hydrogen atom in a silicon lattice, and the ionization of phosphorus and silicon is about on the order of 100 milli electron volts, and that should be milli, not mil. Okay, compare the ionization energy of a phosphorus atom in silicon to the same atom in a germanium lattice. In other words, we're going to take the same atom, phosphorus, and we're going to change its environment. Now remember that it was easier to ion, a lot easier to break apart sodium chloride in water than it is to break apart sodium chloride or salt in, say, canola oil. Environment counts. Here, environment is characterized by the permittivity. This is the environment, how easy it is to separate charge. Okay, so let's run through this relatively quickly. M0 is the mass in kilograms. This is the electronic charge in coulombs, coulombs to the fourth. The permittivity is going to be given by the units of capacitance, which are farads per centimeter. So permittivity squared is farads per centimeter squared. We're going to break that apart a little bit further, and H, or H bar, the units of Planck's constant, are action, which are given by joule seconds. Is that here? Yeah, joule seconds. Okay, so we break down the farad a little bit further. So we know that C is equal to Q divided by V. Remember I hate to say this, but the queer stands alone. Q is equal to CV, or C is equal to Q over V. Q is coulombs, V is volt. The volt is a joule per coulomb, so we have that the units of F are coulomb squared per joule, and we put all that into our equation for E, and here it is. We have M kilograms, we have coulombs to the fourth right here, we have H bar on the bottom, which is joule seconds. This is H bar, and all of this stuff right here, joule centimeter squared per coulomb to the fourth. Oh, sorry, joule squared per coulomb to the fourth is farads. And where does the centimeter squared come from? Oh, okay, it's right here, because the units of E0 are farad per centimeter squared. So all of this stuff actually is permittivity squared. And so if we cancel everything out that we can't cancel, we have coulombs coming down, the coulombs cancel out, the joules cancel out, and the second squared come down here. And of course, what's this? Well, we do it explicitly. I hopefully wouldn't have to do that, but this is energy. Kilogram centimeter per second squared is force, multiplied by centimeter is energy. So this is force, and we multiply by centimeters, and we have energy. So indeed, the units on the right-hand side are the units of energy. So that's comforting. Now let's put all the numbers in. Okay, let's go back here again. For M, E, all the numbers we put in, and let's see how that works. Okay, this is the rest mass, 9.110 to the minus 31 kilograms. This is the electronic charge, 1.6 to the 19th, raised to the fourth power. This is the permittivity squared. This is permittivity of free space squared. The 2 comes down, and this is Planck's constant divided by 2 pi, and we square that, and we use for n 1 for the ground state. This is the ground state, and if we say how much energy does it take to completely ionize an electron, in other words, flip the electron or strip it off of the atom, we would just subtract this to when n goes to 0, and of course then, not n goes to 0, n goes to infinity, and then we would have 0. So this basically is the ionization energy in joules. We divide that by joules per electron volts. That should be volts here, not mole. Sorry about that. And we get 13.56. Okay, in the following assumptions in our model, we said the phosphorus atom displaces a silicon atom, and of course that is indeed the case. And the phosphorus atom has an extra electron to donate to the lattice, and the silicon atoms surrounding the phosphorus polarize due to the relatively high dielectric constant, which facilitates the ionization of the phosphorus. So in a silicon lattice, going back up here someplace, instead of E0, we have E0 multiplied by the relative dielectric constant, which for silicon is 12. So we just basically take this number here and we multiply it by 12 and we square it. So we take the 13.56 and we divide it by about 12, or in this case I made it exact, 11.7, doesn't matter. Generally round up to 12 for silicon, and we get about 0.1 eV, or about 100 millivolts. And we're going to see that that more or less is reasonable for most, for silicon in this particular case. And the dielectric constant of germanium is 15.8. So 15.8 we would divide not by 12 but by about 16, and we would get that it is easier to for a phosphorus atom. That's what phosphorus. I get confused myself. Sorry about that. It's easier for a phosphorus atom to donate its electron to germanium than it is for the phosphorus atom to donate its electron to silicon. And that indeed is the case. It's about 55 millivolts according to the model. 55 milli-electron volts. Now here's the real experiment. For phosphorus, it's not 100, it's about 44. But for germanium, that's for phosphorus donating an electron to a silicon lattice, the model says it's 100. The data says it's about 44. But for germanium, it's about 1/3 to 1/4 less, and that makes sense. Here it's about 1/2, but it's less. It's going in the right direction. And for arsenic, which is also an acceptor, notice that the numbers are not, also a donor, notice that numbers are not all that different. Even though arsenic is further down in the periodic table than silicon. It is the environment rather than the position in the periodic table which determines the ionization energy, the energy that it takes to, in this case for donor, to strip off an electron into the conduction band. And for germanium, they're literally the same. So that is, I think, a very good indication that our model is correct. And for acceptors, it also works. Same thing for boron. Notice that for boron, again, the ionization energy is less in germanium than it is in silicon. And here we notice this is an interesting correlation. These are the electron energies here. The model says about 100 millieV. The data says about 50 millieV. But in germanium, the electron state is closer to the conduction band edge, and the band gap in germanium is somewhat less than the band gap in silicon, and that seems to correlate with permittivities. And if we correlate that with carbon, which is one up in the row than silicon, we find the band gap there is huge, 5.5 eV. Rather than 1.1, it's 5.5, and its dielectric constant is also about 5.5. So the dielectric constant of diamond is significantly less than dielectric constant of silicon, and much, much less, 1/3 the dielectric constant of germanium. And it works out that for diamond donors, you can put phosphorus into diamond, or we can put acceptors into diamond, and we'll find that their energy levels are 0.5 eV, not 50 to 100 milli-electron volts, but a half an electron volts, either below or above the conduction bands. So the trend seems to be rather clear and dramatic, and we'll see if we can understand that perhaps a little bit later in our sessions. Okay, we're going to now instead of going into diffusion current, I didn't think we'd have time to go into diffusion current. We'll start with some thoughts on the density of states in our next session, and we'll skip to the end. What did I have for the end here? Ah, yes, wonderful video clip. This is, I call this Restoring a Soul, and it's the finale to the really marvelous movie Brothers Karamazov. The book Brothers Karamazov, which is one of my favorite novels, ends with the wonderful Sermon on the Stone, and I just implore you to get the book. And it's pretty long, it's about 600 pages, but if you're going to read any part of the book, just read the last 2 or 3 pages, the Sermon on the Stone. It is just overwhelmingly powerful. The movie ends in a completely different way, just like we saw for Lilium versus Carousel. The movie and the play have different endings, but they're both equally powerful. So we're going to see, I believe it's Yul Brynner as Dmitri, a very young, what's his name? Oh, Bill Shatner as Alusha. And I think this clip basically stands for itself. We don't need to see the whole movie, but try to understand how marvelously powerful this is. It's a fabulous ending. So we'll see you next time.
Half your money. The rest when you get to the border. Here's the passport, the money, the train tickets.
Did Ivan arrange this?
Yes.
And do you approve?
Yes. Because you're innocent.
I must see someone first.
They'll be hunting us now. Miss, there's no time.
Please.
No, this comes first. Driver? You remember me?
I'm leaving. You can't leave. Give me the rest of the money.
They can't cross the border without you.
I owe you an apology, Captain. I've come to pay it.
The apology is not necessary for me, but for the boy. Just lie. We have a visitor, son.
Good evening. I brought you something. Artillery. It fires with a frightening noise. Medal.
Take the gift, son.
No, Papa.
He's right. Gifts cannot buy back an insult. Captain, I humbly beg your pardon. I challenged you to a duel. I was a coward. I knew your reputation in the army as a marksman. You could have killed me with the first shot. I am no match for you, Captain. Please, forgive me and release me from my challenge.
Well, son, decide.
Forgive him, Father. Spare his life.
Thank you, sir.
Father, how proud I am